I've got a nice experiment to show you today, and one that we might describe as a physics toy. I thought I'd make this video because I'm surprised by how many people have not seen this before. So, this toy goes under the name of Newton's Cradle. I don't think there's any evidence whatsoever that Newton built one, but he certainly referred to some of the physics that's in it. So, what I'd like to do today is show you some of the experiments you can do with Newton's Cradle and try and explain the results. If you'd like to play with one of these at home, they're quite easy to buy from the usual places on the internet. But if you do buy one, buy a good one and spend the money. This is not a very good one and doesn't work particularly well, but it works well enough for this demonstration. Well, the first problem to solve is many sites call these perpetual motion machines. They're nothing of the sort, and they don't exist, even if some YouTubers seem to believe they can make them. But there are a number of really interesting experiments we can do with this. And what we're going to start off by doing is lifting one ball and crashing it into the remaining four, and asking ourselves, what do you think will happen? So let's see what happens when we release one ball into the other four. Surely they'll all get pushed out of the way. And the result you get is quite surprising. That in fact what happens is the middle three tend to stay where they are, and it's only the outer ball, the fourth one, that gets pushed out of the way. On a really good Newton's Cradle, it's very clear. The middle three stay absolutely where they are, and it's only the fourth ball that tends to move. This is going to take a little bit of explaining. So, now we've done that, why don't we release two balls in? And I think you'll probably guess what happens here. So here goes with two of them. And you can see that the middle ball of the three stays where it is, and the outer two gets pushed out of the way. Because this is not a very good Newton's Cradle, the middle one begins to swing, but to begin with, it pretty much stays where it is. So I think you've got the general idea now, but what happens if we send three balls in? Now this really is quite surprising. So what you'll notice is three go in and three go out. And then going the other way, the three come back in and three go out. Again, this cradle's not a particularly good one, but to begin with, you can certainly see that those three come in and three leave. So the next thing to do, of course, is to see what happens when we release four balls into the system. So here goes with four balls. And this really is surprising. As you might guess, four go in and four go out. And there's a good physics explanation for this. Now, without wanting to state the obvious, of course, what happens if we send five in? Well, of course, the five come out the other side. It's much as you'd expect. But it doesn't go on forever. It will slow down after a while. This is not a perpetual motion machine. Now, before we dive into an explanation, it might be a good idea to try a few other things that you can do with this. If we raise two balls from either side, I wonder what will happen now. Again, the three stay where they are, and each ball goes in and comes back out again. So, I'm sure you can guess what happens now if we send two balls in from each side. But of all the experiments I particularly enjoy, it's this one. What happens if we send two in and three in? Remembering there's only five balls to play with here. It's rather nice that you notice they swap sides. It goes 2 to 3 and then 3 to 2, etc., which is rather nice. And finally, of course, it wouldn't be complete without doing four balls in from one side and one from the other. So if you buy one of these, the experiment that most people do first is the one ball in, one ball out experiment. And they notice a few things. If one ball goes in, one always comes out the other side, and that the energy does seem to dissipate. It's not a perpetual motion machine. But two balls in, two out from the other side, etc. There must be some good physics explanation of this, and that's what I'd like to do next. As with all physics, there's an easy explanation which explains just about everything you see. There, of course, is always a much more complex explanation that deals with the fine little details that we don't quite see, particularly looking at issues like the gaps that might be between the balls, etc. But I think today, let's go with the easy explanation, or at least the easy-ish explanation, which explains just about everything we see. So you need 2 bits of physics for this: conservation of energy and conservation of momentum. And you need to know one other thing, that the collisions here are generally what we call elastic. In other words, when we send in one of the balls with kinetic energy, it transfers all of its kinetic energy to the system. Also, momentum, that if we send a ball in, it transfers all its momentum to the remaining system. There are some losses, but we're going to ignore those. So, momentum. Some of you will know that it's mass times velocity. In other words, one mass comes in with a velocity, and if that's to be conserved, one of the things that should happen, though doesn't have to, is one mass goes out with the same velocity. 2 masses come in with a velocity, and 2 masses go out with the same velocity. But I can think of some of you saying, but hang on, couldn't one mass go in and 2 masses come in with half the velocity? And that indeed would be fine. You're conserving momentum. But we've got to conserve kinetic energy as well, which means that half times the mass times the velocity squared of this one must be the same, which basically suggests that when this one comes in with a certain speed and mass, you're going to get the same speed and mass coming out of this side. I'm not going to draw maths equations, etc., but I'm just going to say that that happens because we're conserving momentum and kinetic energy, because it's an elastic collision. And in elastic collisions, kinetic energy is conserved. So I think we've got it now. Kinetic energy and momentum are conserved in this. They obey the laws of physics. And kinetic energy being conserved means an elastic collision, and conserved means we don't lose any. If we don't lose any kinetic energy, then the kinetic energy into the system is the same as the kinetic energy coming out the other side, and the momentum going into the system is the same as the momentum going out the other side. So, if we send in 2 balls, they have kinetic energy, which must be the same after the collisions. They have momentum that must be the same after the collisions. And the only solution to that will be that 2 balls go in with a speed and 2 balls come out with the same speed. So you've got a good understanding now of how things happen in this. And obviously, if we're going to conserve momentum and kinetic energy, 3 balls coming in must produce 3 going out. And the experiment with 4 balls coming in, 4 must come out. But of course, momentum is a vector quantity. It has direction as well, whereas kinetic energy is not a vector quantity, so it doesn't have a plus and minus in front of it. So this has got momentum coming in this way, these 2 come in this way, and if these 2 come in the opposite direction, there's a positive momentum and a negative momentum, so the total momentum must be 0, but the kinetic energy still remains. So, if I haven't succeeded in baffling you with my average explanation, I'd like those of you who are a bit more advanced in physics to give a little bit of thought to 2 other things. Firstly, when this is up and running, the oscillation's amplitude decays. In other words, it appears to lose energy, or at least get slower and slower and slower. Give some thought to why that might be. And secondly, and this is a complicated one, if momentum is conserved, surely that's positive momentum. In other words, it's acting in that direction. So how do you explain that this ball starts moving in this direction, which must be negative momentum? There's a really good explanation for that, but I am sort of making the point that the momentum in this system, even if one ball goes in and one goes out, is not constant. The momentum does actually change. And you need a little bit more physics to explain that, but you might want to comment on why you think that is. So, that's Newton's Cradle. It's a lovely little toy. It's got some really good physics in it, and it gives us some really good talking points when we're teaching physics. I do hope you enjoyed that video. Do please get one of these from the internet sometime and have a play. Let me know how you get on, and I'll see you next time.